In this video, we're going to simulate neighborhoods. More specifically, we're going to see how people's individual biases and choices for wanting to live next to similar looking people, which we'll call a racial bias, shapes the entire neighborhood as a whole. So, here's our little plot of land. First, let's just randomly populate it with these red and blue creatures. Now, we'll also need to define what counts as a neighborhood for these guys. Basically, each person's neighborhood will be a 3x3 grid, so the 8 other people surrounding them. Then what we'll do is give each one of them a bias to want to live in a neighborhood that is, let's say, 50% the same color as them. Every one of these guys are satisfied as long as their neighborhood meets that 50% threshold. So they would be equally satisfied in a neighborhood with 50% similarity as one with 90% similarity. The rules for the simulation itself is simple. If one of these agents is unsatisfied in their 3x3 grid or neighborhood, they will randomly move to a new empty spot on this plot of land. With each iteration of the simulation, we're also going to be tracking the overall level of segregation over the entire landscape, as well as the percentage of people unsatisfied in their neighborhoods. Let's see what happens. Okay, after 21 iterations of people moving around until they're happy, we've settled on this orientation. What's interesting though is that if you look at the overall level of segregation in this society, it's 86.69%, which is significantly higher than what any individual wanted in their own neighborhoods. This brings us to an important point. Individual decisions on a micro level can aggregate in unpredictable ways to create unexpected results in the system as a whole. But let's push this further. What if we reduce the individual bias to 26%? Again, we see similar results. The overall level of segregation is significantly higher. In fact, it's not that much different from the level of segregation we saw when the individual bias was at 50%. So even though the individual bias decreased significantly, the overall level of segregation didn't. Now, let's run this one more time. So let's make it a nice round 25% instead, and see what happens. Decreasing the level of individual bias by just 1%, we significantly decrease the overall level of segregation. This is what I mean when I say that individual biases can aggregate in unexpected ways. In fact, this notion of small changes causing a huge impact is called a tipping point, a sudden spike of sorts. If we graph the different levels of biases against the overall level of segregation, we can see exactly where the tipping points are. What's special about these percentages? Why does the tipping point occur at around 25%? But they're really not special, universal percentages. They're just a function of the specific choices we made when constructing the simulation, such as how we define the neighborhood to be a 3x3 grid. Now, it goes without saying that this model is very, very simple. It was originally devised by Thomas Schelling, a Nobel Prize-winning economist back in 1971. It has, however, been used as a basis to build more complicated models, ones that take into account factors such as income, wealth, and housing quality. Research has been able to mimic real-life residential patterns and also explain how very slight biases can create negative outcomes for marginalized communities where they end up paying higher prices for the same quality of houses. Maybe this is something we can explore in another video. The key takeaway though is understanding how individual biases can aggregate, can turn into something greater than just the sum of its parts.